All right, so in the video that I'm asking you to watch over the weekend, these last few trends are going to be talked about. I want to take just these last 5 minutes and talk about some trends that we can get, some ones that are pretty easy to understand, and don't have any exceptions associated with any of them. So the first one that we're going to talk about is magnetism. Magnetism is the ability of an element to be attracted to a magnetic field. And the property of magnetism comes down to configurations. In order for something to be magnetic, it has to have free electrons. In particular, electrons that are unpaired in its configuration. So one of the reasons that iron is magnetic is if we look at its electron configuration, we see all of these unpaired electrons in it, and those unpaired electrons are able to interact with the magnetic field. Something like zinc is not magnetic, and the reason it's not magnetic is you can see that every single one of its electrons are paired up. And so while those electrons would exhibit their own fields, because they are paired with electrons that are going in the opposite direction, those fields destroy each other, and there's no net electric or magnetic field being generated from them. The idea of magnetism can also extend to ions as well. So in addition to titanium being magnetic, titanium 2 ion is also magnetic because both contain unpaired electrons within them. And so this does introduce an interesting phenomenon where it is actually possible that you could have an ion that is magnetic coming from a metal that is not, or vice versa. Having a metallic ion that is diamagnetic, even though the element itself is paramagnetic. So you're not going to see magnetism on the quiz or on the exam next Friday. Where this might show up is, this is a great question that they love to pull for the final, where you can just be very quick. Which of these elements is paramagnetic? And the answer to that, you just go to which one has unpaired which one has unpaired electrons. Another trend that is interesting for us, and why I bring it up here, is because a lot of the other properties that we talk about can be explained through this thing called effective nuclear charge. Effective nuclear charge is best described as kind of the level of attraction that is felt by the electrons toward the nucleus. And what we have in effective nuclear charge is a large interplay. We have the interplay of the attraction between protons and electrons, and also the interplay of the electrons repelling each other in the electron cloud. Those two forces are competing with one another. And effective nuclear charge helps us to kind of quantify how much of that competition is present and what the overall net effect is. We can estimate effective nuclear charge by taking the atomic number of an atom and subtracting from it the number of core electrons in that atom. And so that's what S is. S can be referred to as the shielding constant or the screening constant. But the basic idea behind S is it's the number of core electrons. The more core electrons there are, the better shielding is going to be present. Quick example, just to give you a visual here. If we can imagine this classroom as an atom, and this part here being the nucleus, each of these rows of desks representing energy levels, it's very easy to see that the people sitting in the front row in this first energy level are going to have the least distance between myself and them, And if we were talking about attractive forces, those attractive forces would be the greatest between the nucleus and that first energy level because of their close proximity. If I wanted to walk over to Isaac and slap him in the face today, it'd be pretty easy to do so because he's right there. If I want to do the same thing to CT back there, it's going to require a lot more effort on my part because he's a lot further away. I'd have to shorten the distance between myself and him to get to him. That's the shielding effect. The more stuff that is in the way, the harder it is to have an impact as far as attraction is concerned. Those electrons in the back are held a lot less tightly than the electrons in the front. And that plays out in terms of atomic size because we can look at two different factors. The first, energy levels. The more energy levels you add, the greater the distance becomes. So we can see that there is a physically larger distance between myself in the fourth row compared to myself in the third row, compared to myself in the second row. So that is a columnar trend. As you go down a column, more energy levels become apparent, the atoms get bigger. The horizontal trend has to do with repulsion versus attraction. Inside of that energy level, you can pack as many electrons as you want in there. The thing to remember is that the protons the nucleus is getting bigger as well. So even though you're adding more electrons, they're not getting any further away, but yet the nucleus is getting larger and more attractive. And so the net result is that those electrons are getting pulled on by this stronger nucleus and they're getting drawn closer. So as you go across, you see that the atoms get smaller and smaller and smaller because of that. And so we can see this pictorially here through this graph. All right, so we're going to end our discussion with module 3 here, just looking at these last couple of periodic trends and recognizing some of the patterns that exist into them and how we can use the periodic table to kind of work our way through those. And so if you recall from the previous lecture where we ended, we talked about two of those trends. We talked about the idea of magnetic behavior, and we also talked about effective nuclear charge and how we can use effective nuclear charge to talk about atomic size and the trends that exist in terms of when you go down a period, things get bigger, and when you go down a group, things get bigger, and when you go across a period, things get smaller. So what we want to focus on in this stage here is we want to look at ionic size. So this is the next trend that we're interested in. And when it comes to ionic size, there are kind of two divergent pathways that we look at. First of all, we want to do comparisons of ions to the atoms that they came from. And so the first thing that we would want to notice is that when it comes to cations, those cations are smaller than the atoms that they came from. So that's the first thing that we want to notice, is that by taking away those electrons, we are seeing that the ion that forms is indeed smaller than the atom that it came from. We see that here with all of the metals. And in some cases, that can be a really drastic difference, especially as our charge increases. The other thing that we want to look at is that anions, that is negatively charged ions, are considerably bigger. Why are they bigger? Well, we've got more electrons in the same space. We haven't increased the number of protons, so we've got greater repulsion. So once again, the thing that we talked about that kind of led us into this, the idea of effective nuclear charge, that interplay between the attractive forces in the nucleus and how they attract the electrons, and the repulsive forces that exist between the electrons themselves, this plays out really, really, really finely here. Because with the cations being smaller, why is that the case? We have fewer electrons present, and so we get more attraction between the nucleus and the electrons. And why are the anions bigger? Well, for much the same reason. The anions are bigger than their parents. The anions are bigger than their parents because we now have more electrons, and so we have more repulsive forces between the electrons and themselves. And so the natural tendency is that that atom is going to expand because of those repulsions. And again, the expansions here are usually quite significant. There's another trend that we can investigate, and that trend is associated with what is called the isoelectronic series. So we talked a little bit about the isoelectric phenomenon when we started looking at ions and comparing ions and their electron configurations to other ions. Isoelectronic series are when we have either atoms or ions that have the same number of same number of electrons in them, but differing numbers of protons. And the way that it goes is, again, a matter of attraction. Since we are talking about equal numbers of electrons, it's going to be the proton number that dictates attraction. And so more protons equals more attraction, and greater attraction is going to lead to smaller species. So if I compare sodium ion, magnesium ion, neon, oxide, and fluoride ions, all of them have 10 electrons, but the order of size is going to be based upon the number of protons. Magnesium will be the smallest because it has 12 protons. Sodium has 11, neon 10, fluoride 9, and oxide 8. The more electrons, the more protons you have, the greater the attraction is going to be. That greater attraction is going to lead to smaller ions as a result. So that's the trend of ionic size. And again, it's kind of twofold. We're comparing the ion itself to its parent atom, and then we're also looking at an isoelectronic series. The third trend that we want to look at is ionization energy. Now, generally speaking, ionization energy is directly inverse to atomic size. Small atoms are going to be harder to ionize. Large atoms are going to be easier to ionize. What is ionization energy? Ionization energy is the energy required to remove an electron from an atom or from an ion. So since we're always talking about positive energy, it's going to require energy to take that electron and promote it up to and through the outermost energy level. Size does make a difference here. Bigger atoms are going to be easier to ionize because they have less pull, less hold on those electrons. Smaller atoms are going to be difficult to ionize because those electrons are being held more tightly. It's all about attraction here. So we can take that idea of size and generally apply it in the opposite direction toward energy. Now, there are a couple of weird states here, a couple of configuration-based anomalies. If I'm looking at group 2 versus group 13, so the group 2 configuration looks like this, where it is S2 and P0. The group 13 configuration looks like this. It's S2 and P1. Well, we talked about this a little bit when we looked at configuration-based anomalies related to, like, D4 atoms or D9 atoms. There's just something about having a completely filled sublevel that increases the stability of an atom. And so with this completely filled sublevel here, this electron is actually harder to remove than this electron. And so for that reason, elements in group 13 actually have a lower ionization energy than those in group 2, even though they are smaller. The other anomaly exists between group 15 and 16. In group 15, we've got S2P3 as its configuration. In group 16, we've got S2P4 as the configuration. And what it comes down to is the change between removing this electron versus removing that one. And again, for some reason, the idea of balance in sublevels is extremely valuable to atoms themselves. And so by removing this electron in the P sublevel in the group 16, we go from a P4 configuration to a P3. So we go down to a balanced p orbital subsystem. And that is more attractive than unbalancing that P sublevel by taking away this electron here. So there we have kind of the big differences here as far as ionization energy is concerned. For the most part, ionization energy is the flip, the inverse of atomic size. But there are a couple of exceptions here, and they're all related to the filling or unfilling of that P sublevel. And we can see that change kind of showing up here in this graphing diagram here. So here's my group 2 and my group 13. And we can see that the boron group is generally lower in energy than the alkaline earth metals. And we can see the same kind of thing here amongst group 15 and 16. The nitrogen group is generally higher in energy than the oxygen group is. But what we also need to notice here is that those particular trends are very loose. And really seem to be most affected higher up on the periodic table. So in the second energy level, the third energy level, and even to a smaller degree, the fourth energy level. Once we get beyond that, the differences actually become virtually unnoticeable. Another unique trend that we need to make note of when it comes to ionization energy is that there can be multiple ionization energies. So long as there are electrons in a given atom, you can remove them and it will take energy to do so. There are a couple of important notes here, though. First of all, each subsequent ionization energy is going to require a good bit more energy than the one before it. Now, the reason for that is pretty simple. It's attraction. As I'm removing electrons, the remaining electrons, because of that loss of repulsion from that electron leaving, are going to be even more drawn to that nucleus. That nucleus is going to have more and more power over the remaining electrons that stayed as electrons go. And so it's going to be harder and harder and harder to remove the next one. The other trend that we want to notice is that when we get to a noble gas configuration, there is a noticeable jump in energy to remove that next electron. So we take a look at lithium. Lithium has one valence electron. Its initial ionization energy is 517. Okay, whatever. Once I remove that electron, though, lithium has a electron configuration now of helium. And helium is completely full in its energy level. So removing that next one, I'm now taking electrons from a lower energy level than I did before. So if I look again, from a configuration standpoint, when I remove this first electron from lithium, it was 1s2, 2s1. Now it's just 1s2. And so I'm not stealing from the second energy level now. I'm now stealing from the first. Notice that I've got a big bump in energy as a result. With beryllium, beryllium's 1s2, 2s2. So the first ionization energy, not bad, bigger than lithium, but we expected that based on size. The configuration here, 1s2, 2s1. We see a bump in energy, but it's not a significant bump. It's about what we would expect. And now we have just 1s2, and notice that the bump is considerable there. So every time we clear out an energy level, the next ionization energy takes a considerable hike. And we need to make note of this because it is that important. When we jump down to a lower energy level, we're really seeing a very large increase in the attraction between those atoms, or excuse me, those electrons and the nucleus. So let's take a look at an example problem here. So this example problem comes from Top Hat. Now this example problem is not going to be assigned to you. We're just going to do it here as a matter of principle and practice. Sort these atoms according to ionization energy. There are a total of 7 of them. So we are looking at helium, boron, lithium, carbon, fluorine, neon, and oxygen. Now, highest on top, smallest on the bottom. So the highest one is going to be the smallest one, and the smallest ionization energy is going to be the biggest atom. So looking at these, I can see helium is in the first energy level. None of these other ones are. So I'm going to rank helium as having the highest ionization energy. From there, I see lithium, boron, carbon, fluorine, neon, oxygen. All of these are in the second energy level. So we want to put them in order of biggest to smallest as well. And so that order would be, the biggest of them would be the lithium, followed by the boron, followed by the carbon, followed by the oxygen, followed by the fluorine, followed by the neon. Neon would be the smallest of these. Lithium would be the largest of these. Now, I need to look and see, are there any exceptions in this list? And the answer is no. The exceptions would have been beryllium and boron, which we're not ranking beryllium, so that's okay. And nitrogen to oxygen, and again, we're not ranking that one, so it's okay. So I just need to put these in reverse order. So that means that the neon would be the next one, then the fluorine, then the oxygen, then the carbon, then the boron, then the lithium. That would be the correct order. Because again, without exceptions to cloud things up here, ionization energy is just a matter of size. The atoms that are the smallest are going to have the highest ionization energy. The atoms that are the largest are going to have the lowest ionization energy. The last trend that we will talk about isn't really a trend. It's just a property, a phenomenon. It's called electron affinity. Electron affinity you can kind of think of as the opposite of ionization energy. So ionization energy was how much energy does it take to pull an electron out? Electron affinity is how much energy is released when an electron gets put in. And for the most part, there aren't a whole lot of great trends that exist. Most electron affinities are negative, meaning that when we add that electron, it does release energy. However, there isn't a whole lot of great trending that goes on, other than we can point to that there are some groups that are more likely to accept an electron than others. So, and if we think about it from an electron configuration standpoint, it makes sense. So group 7A, group 17, the halogens, those ones are going to have the most negative electron affinities because they're adding that electron is going to help them to get to a noble gas configuration, fill out their energy level, and that's what they're going for. That's what they want to do. Group 1. Group 1 has surprisingly large negative values for its electron affinity. And why? Well, in adding that electron, it fills the s sublevel. We can see something very similar here with group 14. Group 14 has considerably higher electron affinities than what would be expected for nonmetals, because again, in doing so, it's filling up, it's half filling the p sublevel for its energy level. Whereas group 15, the nitrogen group, these are lower than expected, and they're lower than expected because their p sublevel is already half filled, and adding an electron actually disrupts that balance. All right, last notes that we want to make for this particular module, consider chemical behavior and qualities. And we just want to talk just a little bit about these two individually. The first thing is we want to look at metallic behavior or metallic character. Metallic character can be applied to any element, and it's an affinity or a capability, the kind of general need to lose electrons. And we see that as we go from right to left, so from the metal side of the table to the non-metal side, and from the top to the bottom, we tend to see increases in metallic character. So metals tend to congregate on the left-hand side of the table, no shock to any of us, but metallic character also increases as we go down a group. So potassium is more metallic in its properties than sodium is. Sodium is more metallic than lithium. And all of them are more metallic than chlorine. The other thing that we want to look at is this chemical behavior. As we find things that tend to be more and more metallic, we also tend to find that when they make oxides, those oxides tend to be more basic. So substances with high metallic characters also tend to be basic. And the more metallic it is, the more basic the compound becomes. Things that are not metallic tend to form things that are not basic, and they actually will start to trend toward the acidic side of the ledger when they make oxides. So just as a base of comparison here, we've got sodium oxide. Sodium oxide, when reacting with water, will make sodium hydroxide, which is a really strong base. Whereas dichlorine heptoxide, Cl2O7 here, when it reacts with water, will make perchloric acid, which is a strong acid. So the more metallic something is, the more basic it's going to be in its oxide behavior. The less metallic something is, the more acidic it's going to be in its behavior. So that is all for this abbreviated kind of wrap-up session with Module 3. If you have any questions, feel free to drop those in the active feedback for this module, or drop me an email or text anytime this weekend and we can go through those. But until next time, I will see you in class.